Good morning, afternoon, ladies and gentlemen, whatever time it is. I'm re-recording this video because the first one was too long. I'm breaking this into 2 days, Intro to Calculus number 1. First thing you need to do, and if you don't have it next to you, you're going to have to hit pause, but please go grab your calculator. There's a few settings we need to check in your calculator to make things easy, and we're going to enter this graph that you see in there. So make sure you grab your calculator. First thing we're going to do before I do anything is I'm just going to go home. Okay, first thing you want to do is you want to hit number 5, your settings. And you want to go to number 2, document settings. And within that, the display digits right here, make sure you are on float, not float 1, 2, 3. You're not on any of these. Okay, you want to be on float. Reason we want to be on float, that's going to give us the most decimal places that we can have in this on the calculator, and it's very imperative everything we do is rounded to 3 decimal places. Okay, here's also when you get into trig, you might have to flip-flop between radians or degrees. Typically we're always in radians. Okay, but main thing is make sure your display digits are on float. Everything else should be good. Make sure you click that to make your default. Hit OK. And then we're going to go do a new document. Nope, not going to keep that one. And in that new document, we want to add a graph. Okay, and in that graph, we are going to enter this x cubed minus 2x squared minus 5x plus 6. So I'm going to come over here and I'm going to say x cubed. I'm going to enter over, then we're going to say minus 2x squared minus 5x plus 6. And we're going to hit enter so we can see our graph, okay? One of the first things we're going to have to be able to do is we're going to, if you don't remember, okay, I don't like this on here unless I have multiple graphs, but if you highlight that and you actually hit delete, it'll take it off, but your graph will stay there, so it's not on there. Obviously, we want to see our whole graph in there. Well, everybody knows there's a few different ways to do it. You can double tap that up there, and you can change the settings from up there and do it one at a time, or you can go into your settings. Okay. By that I mean you can say menu. We want to do a number 4, a window zoom. And number 1, window settings, and then you can change your X min, X max, any of those. You can also change your scale, all of that. I usually go into there, but this time I only needed to change 1. Also, now that we're in a graph, you want to hit menu because decimals are just as important in graph, and this isn't going to be defaulted to float. So when you hit menu, when you're in the graph screen, hit number 9 for settings, and make sure this is just for graphs and geometry settings. Make sure your display digits are on float, okay? Not anything else other than float. The other crafty little critter in these CAS, in the CAS model is make sure this guy right here automatically find points of interest. This is really nice. You'll see why I'm talking about it. Make sure that is highlighted or checked off. Show axes and end values, you don't have to have that, but to automatically find points. Make that your default. Apply your settings. Okay, so what we're going to be doing in here is we're just going to be looking at using our calculator to find a few pieces and parts of the graph. So I'm going to close this down. X-intercepts, okay? Well, we all know what x-intercepts are. We need to be able to tell our calculator how to find them. Okay, x-intercepts, remember algebraically, that is when y equals 0. So if you plug in 0 for your y, solve for x, you will have your x-intercepts. Another way to get that in your graph is you hit menu, analyze graph, 0. You might hear me say sometime menu 61. That means hit menu, hit 6, hit 1, and it automatically takes you into finding zeros in your graph, okay? Also, we're going to look for y-intercepts. Well, to find y-intercepts, that's when x equals 0 algebraically, and then you solve for y. Remember, you can only ever have one y-intercept, but you can have multiple x-intercepts. Well, that's menu, trace, trace graph, and after you hit trace graph, you're going to hit enter 0, okay? And that's going to take you straight to the y-intercept on your graph. I'll show you why that setting was on there, okay? Well, if we come back here and, come on, baby, and I brought that up, okay, I can find my x-intercepts if I wish by saying menu, analyze graph, find zeros. Well, then it tells me lower bound. That means I need to get on the left side of the 0 I want. You have to use your toggle, your little left and right arrows to get over there. And then we got to get in the upper bound or the right side of that 0. And it will drop that point for us really nice. And we can grab that with the little hand. We can drag them around, okay? Now, remember I had you type in there to find enter points of interest on the graph. This is why I did that. If you hit menu, trace, and you hit trace graph, it automatically goes on there. Check it out where it put me on 0,6 in the bottom right corner. That's my y-intercept. And as I toggle right and left, check it out, it's finding a maximum, a point of interest. It's not always going to find it right away. This time it did. And it's also going to stop on my zeros. So as I'm coming across, as I'm toggling here with my trace feature, when it stops and it says maximum, if I want to know and I want that point to stay on there, if you just hit enter, it'll drop that dot on there and we are still in trace. So I can come along, and the y-intercept is another point of interest. I can hit enter there and it drops it to 0,6, and I can keep going. Oh, there's another 0 at 1,0. If I hit enter, it'll drop it, and I can keep going around. Oh, there's the minimum. And I can find, oh, my other 0, I went past it, and I'm going to hit it, and I'm going to enter my 0 on there. Now, remember, you can grab that little hand, and you can move. Come on. Uh-oh. I didn't like that. I got to use my undo button now. Let me use my control undo to put it back, and I want to grab that guy, move him there. That one's fine. Come on, grab it. And then I'm going to take this maximum, maybe over here, but we will always be rounding accurately to 3 decimal places. So make sure you're in there. But that's how you find your maxes and mins if you have forgotten. Okay. The next thing we are going to take a little gander at here is we're going to take a little gander at symmetry. Okay. Back in the pre-calc in Alg 2, there's actually 2 types of symmetry. We either have y-axis symmetry or we have origin symmetry. If we don't have one of those 2, we have no symmetry. Trying to refresh your memories a little bit here. Y-axis symmetry, well, what happens is it's an even function. Well, what does that mean? That means if I'm looking at a graph and I completely cut the graph in half right on the y-axis and I fold it over, the left side will lay perfectly on top of the right side. That is y-axis symmetry. If that ever happens in a graph, okay, it's an even function. Even function means a lot, mainly when we hit integration towards the end of the year. It's going to help us integrate rather than going from -2 to 2. We can integrate from 0 to 2. You'll find out 0 is a nice integrable value to put in there. And we can go from 0 to 2 and double our area. So, well, that's all down the road. What it actually means, y-axis symmetry, is if I put an x in, I get out the y. If I put in the opposite of x, it still spits out that y value, okay? Very common y-axis symmetry function is y equals x squared, the parent function of a parabola. And that is because when I graph this guy, if I made a table of values, I would have 0, 0 in there. And I'd have a 1 in for x, a 1 would come out for y, Conversely, if I put a -1 in for x, I would get a +1 out for y, so I can see that dot. Those points reflect right across the origin. If I went in for a 2, I get 2, 3, 4. And if I put a -2 in, I would get 4. And if I graphed it as best I could, I can see that that graph is it's incredibly symmetrical. If I cut it across that green line, it would fold across and lay right on top of the other function. Or I'm sorry, the other side of the graph. Another super common one not to forget, y equals, not sine x, it's cosine x for an even function. Sorry, sine's an odd function. I come back, y equals cosine x. Reason why it's so beautifully symmetrical, remember graphing your trig functions. When you graphed your trig functions, you always kind of laid a spot out for each point of the unit circle from 0 to 2 pi. And your cosine in the parent function had an amplitude of 1. And your cosine started out at a maximum, then it went to a 0, then it went to a minimum, it came back to a 0, and then it crested back out at a maximum. So we could see that periodic function of a cosine. Now that doesn't look too symmetrical, but if I graphed another period to the left, that little bugger is incredibly symmetrical. And I can see, again, if I folded it right across the y-axis, the left side lays right on top of the right side. It's an even function. Algebraically, we said an even function is if we took f, if we put the opposite of x into f, we got the original function out. People hated that in Alg 2. Not really sure if you did that in pre-calc or not, but that's what it means to be an even function. If I put the opposite of x in, I get the same y out either way. Okay, so f of -x equals f of x. We also have origin symmetry. Origin symmetry means it's an odd function. What that means is if I put, say I get 1 in, I get, say 3 out. Doesn't really matter, but if I went 1, 3, when I put the opposite of x in, -1, I'm going to get the opposite of that y out, -3. And when I plot these 2 points in the coordinate plane, if I connect both of those in the coordinate plane, guess where that line's going to go through? It's going to go through the origin, okay? Hence the name origin symmetry. But when we had origin symmetry, algebraically, I'll hit the part you hated the most from Alg 2, origin symmetry said, if I put the opposite of x in, I got the opposite of y out. Everything changed, okay? So that was an odd function. Well, when I'm looking at that odd function, and I look at some examples of odd functions, okay? Most common one, probably, y equals x cubed. That's odd. The exponent's odd, huh? Funny. Not really. I know it's cheesy. But if I graphed it, if I made that graph, if I can do this, good. I'm going to go through 1. If I put in a 1, I get a 1 out. If I put in a 2, I get an 8 out. I'm going to put that up here. And if I put -1 in, we get -1 out. And if I put -2 in, I got -8 out, which was down here. So that's what my graph looks like, and it comes up like that. That's what your cubic function looked like. But like I said before, if I take a point and its mapped pair over there, if I draw a line through them and I connect them, it will go through the origin every time. Doesn't matter which one it is. It's the map pair. That line will go through the origin. That is an odd function. Another odd function is the y equals sine x. Okay? Trig comes out. We don't have a particular trig unit in this class at all, like you did in pre-calc and algebra 2. This stuff just comes out. And you're expected to, bottom line, remember your trait. We'll work at it though. And again, sine is 1, 2, 3, 4, going around your points in the unit circle. Amplitude of 1, -1. Sine started at 0, then it went to a max, then it went to a min, or excuse me, back to a 0, then it minimized out, and then it stopped back for 1 period. But if we extended back another period, we can see why it's an odd function. Now we're doing everything backwards in the unit circle. And I can see this is like the double flip, if I can say this, okay? I can map these points across, or if for an odd function, if I cut it on the y-axis, flip this side over to here, and then cut the x-axis and flip up, I call it the double flip, you would see one piece of a graph. It's kind of hard to picture, but that's what an odd function does with origin symmetry, okay? Enough odd and even. For instance, if I took a quick second and I looked at the one we graphed, if I took and I sliced this on the y-axis, is that thing symmetrical across the y-axis? It is not. If I took this maximum and this minimum and I connected those through, it didn't go through the origin. It's not even, it's not odd, it's neither, okay? That's what odd and even graphs look like. If you don't have y-axis symmetry, you don't have origin symmetry, it's just neither. This last one, x-axis symmetry, well, if you have x-axis symmetry, then it's straight up not a function. What? We've never done that before. Sure you have. You guys did conic sections, I believe, in pre-calc, right? And when you're looking at the conic sections in pre-calc, let's say we had one of our sideways parabolas, okay? X-axis symmetry. But, because if I slid it there, it would fold over, but it fails the vertical line test, so it's not a function. In calculus, it's a big deal if something's a function or not, okay? We mainly work with functions, and only functions, not non-functions. Okay, conics and stuff will come up in future calculus classes, really not as much in this calculus class as it does, okay? So, that, whoa, get that notebook up there. All right, so I am going to go to my next one. Asymptotes, woo, we love asymptotes, right? What the heck is an asymptote? Well, lots of functions have them. Think rational functions, that's the ones we use a ton in calculus. We use exponentials, logarithmic, okay? But rational functions sometimes have both vertical and horizontal asymptotes. What the heck is a vertical asymptote? A vertical asymptote at x equals some number c happens only if, as x approaches that c value, okay, what happens is y approaches either positive or negative infinity, meaning it goes straight up or straight down. It's really important to understand for a vertical asymptote. That means C, the point C, is not in domain. It's not in the domain of a function. It's an invisible vertical line going straight up. When does that happen? That happens in rational functions when the denominator equals 0. Okay? If I have some number over 0, that equals undefined, remember. We can't divide by 0. That is a vertical asymptote in the graph. Okay? Vertical asymptotes can never be touched or crossed. Okay, important. Vertical asymptotes. Verts can never be touched or crossed. Okay. One big deal, 0 over 0. Okay, 0 over 0 does not equal undefined. I just want to get that out right now. If I have a number or something over 0, it's undefined. 0 over 0 is not undefined. It's going to be called an indeterminate form of a limit when we hit our limits, but we're not to those yet. Okay. Now, I'm going to draw that line off. We're going to look at horizontal asymptotes. Whoa, horizontal asymptotes we did have. Okay. How the heck did we find horizontal asymptotes? We found these by comparing powers of numerator and denominator. That's how we find our horizontal asymptotes in rational functions. Exponential functions, remember, exponential functions have horizontal asymptotes, and that's when they're pretty much running out of everything. But we're just doing these right now to rational functions. This is a little Kruger labeling, and I don't know if you had me in Algebra 2 or not, but I'm going to call it if the power of the numerator is less than the power of the denominator, meaning the denominator has a larger power of x in it than the numerator does, we will have y equals 0 be our horizontal asymptote, the invisible line y equals 0, which is the x-axis. If I have the power of the numerator exactly equal to the power of the denominator, okay, we will have a horizontal asymptote at y equals the lead coefficient of the numerator divided by the lead coefficient of the denominator. All that is the coefficient on the biggest power in the top over the coefficient of the biggest power in the bottom. And if the power of the numerator is greater than the power of the denominator, okay, then there is none. We don't have a horizontal asymptote if the power in the numerator is greater than the bottom, because it takes everything over and it just goes to infinity. Couple quick little examples here I'm just going to sketch out for you. Let's say I have an example. Let's say we have f of x equals x plus 1 over x plus 2. Okay? If I looked at this graph, okay, I can see my denominator will equal 0 at -2. So if I put a -2 in there, I'm going to have what? -1 over 0. So 1, 2. That is going to be a vertical asymptote at x equals -2. My graph will never touch that. If I compare my powers, notice the power of the top, got a 1 there, power of the bottom is a 1. I'm going to take my y equals 1 over 1. So y equals 1 is my horizontal asymptote. Okay? And I can touch a horizontal, and I can and I will. It's going to be somewhere in the interior of the domain. Okay? I can also look at my x-intercepts. I'm going to make my graph green now. If the top, if I put a -1 in there, well, I have an x-intercept then because I get 0 over 1. And this graph is going to go right there, and it's going to go right there, and then the other branch is going to be up here. We could continue to plot a bunch of points, but we don't need to. That is what that's going to look like. I have y equals 1 horizontal asymptote and a vertical asymptote. Verticals, these guys, you will never touch it. You will never cross it. This is never crossed. The closer I get to -2 from the left side, the higher my graph is up here. The closer I get to -2 on the right side, the lower it is. It just keeps going down. But -2 is not in the domain of the function. Okay? There's all kinds of rational functions. They don't have to just have one vertical asymptote. I'm going to throw another example on here for you. And that's going to be f of x equals x squared plus 4x all over x squared minus 9. Well, if I had fun, and I don't want to have fun, I don't want to waste a lot of your time graphing these by longhand because we're really not going to do a lot of that. But I can see at 1, 2, 3, at x equals 3, I'm going to be undefined. And at 1, 2, negative 3, x equals negative 3, I'm going to be undefined, right? I can see that because there's 2 zeros in the denominator. Those are undefined. I can also see y equals 1 is going to be a horizontal asymptote because I'm going to compare the powers of those two, and it's going to be 1 over 1. So then I'm going to make my horizontal asymptote here. And that's going to be y equals 1. From there, I'm going to go green now. I can see my zeros in the numerator. X-intercepts happen when the numerator of a fraction equals 0. If I factored an x out, I'm going to have a 0 at 0, and I'm going to have a 0 at negative 4. Okay? So I already know where 2 of my branches are. I already know, back from pre-calc, back from Algebra 2, back from them all. This one's going to go like that. It's going to get snug as a bug in a rug as I go way out to positive infinity. This top one is going to go like so. And if I plotted a few points in here, this middle guy is actually going to physically touch it and cross, and it's going to go right across that horizontal asymptote. That is legal when I'm talking about the interior of the domain. That will never happen way out here. That will never happen way out here. Okay? And I guess one thing I should have done up here is given us our definition of a horizontal asymptote really quick. And I'll write that in red right underneath that. I have a horizontal, they're end behaviors, remember. I will have a horizontal asymptote at, I'm going to call it y equals b, if as x approaches infinity, and it doesn't matter if it's positive infinity or negative infinity, as I get way out to the end of the graph, if my y value approaches that value of b I'm talking about over here, okay? Doesn't have to touch it. It's going to get really close to it. And that's about it. And I think from there I'm going to do one more thing yet, and then I'm going to call it quits for the day. And, oh crap, come on, my poker. I'm going to go right there. Maximum and minimum points, okay? These are going to be maximum and minimums, high points, low points on our graph, okay? Maximum and minimums happen when, okay? These happen when, how do I want to say this? There is a change in the graph from increasing to decreasing, or from decreasing to increasing. Okay? This is where max and mins happen. Well, obviously, if I change from increasing to decreasing, I have a max. And if I change from decreasing to increasing, I have a min. Okay? How are we going to find those? Menu, analyze graph, max or min. Or we use that nice little trace feature if our calculator is set on finding the important parts, because maxes and mins are important parts. Intervals of increasing and decreasing. Well, this is talking about what part of the domain, and I specifically write domain because we're talking x values, what part of the domain the curve is going up or going down. That's what we're talking about of increasing and decreasing. Okay, up is obviously increasing, down is obviously decreasing. So a quick little sketch here to talk about that is I'm going to make an x-axis. I'm not going to make a y-axis. Why? Because we don't need one. And I'm just going to make a general sketch of kind of a goofy little cubic. And obviously, we can see that there's a maximum and a minimum, right? So if I labeled right here, I can see that's a maximum. And if I labeled over here, that's a minimum, because it's a low point. We will also take these a step further in a while. We will talk about absolute maximums or minimums and relative maximums and minimums. If it's absolute, it is absolutely the highest or lowest point on the graph. When you're looking here saying, hey, Kruger, it's getting higher and higher, there's an absolute maximum out here, the answer is no, there's not, because that's infinity. Infinity means never stop. That's going to keep going higher. There's not a highest point on it, okay? In order to find increasing and decreasing intervals, we find our max and min. And what I'm going to do is I'm going to just jot down, that is going to be, I'm going to call it x sub 1. So this maximum is located at x sub 1 comma y sub 1. We use lots of subscripts in calculus. This minimum, we're going to call that x sub 2. So the actual location of this point would be x2 comma y2. And I'm just using a 2 showing this point here is different from that point there. And all we're going to do is we are going to look to say, hey, when is the function increasing? Obviously, a function is increasing as you read the graph from left to right when it goes up. I'm increasing all the way up to that maximum. Then left to right, I go down, so I am now decreasing. And then I stop decreasing and I increase again. And when we're writing our intervals of increasing and decreasing, okay, it's imperative we use the domain values. Okay, so when I'm writing this function as increasing, its intervals of increasing, I would say increasing, this function increases and then it decreases. I can see there's two of them. The interval of increasing, okay, let's check this out. Way down here is negative infinity for the x's. And then I get to my x1, my x2, somewhere in the middle there's a 0, and way out to the right is positive infinity. So left to right, small to big, I'm increasing beginning at negative infinity all the way up to my point x sub 1. At that point x sub 1, I kind of stop increasing and I begin decreasing from x sub 1 all the way to x sub 2. And when I hit the x sub 2 right here, well then I start increasing. So then I have a union, because I have two intervals of increasing. I have a union of the two at x sub 2, and it never quits until I get to positive infinity. Now I know if somebody was in class, they're going to say, hey, Mr. Kruger, that whole parenthesis, bracket business, do I have to use that? When we're talking about intervals of increasing and decreasing, the AP board does not care if you use brackets or parentheses. They do care if you put a bracket. Infinities never, ever, ever get brackets. Okay? So if you go solid parentheses, always on increasing and decreasing intervals, you will never get them wrong in the AP board. Okay? What happens, Mr. Kruger, if I forget my union in there? Yep. I'll mark it wrong. It's important to have your union showing that it's the union of all these intervals of where it's increasing, okay? From there, we will pick it up on inflection points quick tomorrow and go through a couple examples, and then we will be done so you can do the homework. Talk to you tomorrow.